Okay, so one of the applications of playing with surds is to simplify the surd. So we're looking at something like the square root of 40. Is that its most simplest form? And what we're trying to do is really get the perfect squares out of it. Now, we play with it this way. If we look at square root of 40, we can say, well, that'd be the square root of 4 times the square root of 10. Now, why have I picked square root of 4 and the square root of 10? Well, really because I'm looking at 40 and I'm looking for factors that are perfect squares. So you want your factors there of 40, and are there any perfect squares? So if there's any perfect squares, we can start to simplify it, because they can come down to a much simpler form, or not much simpler, but a simpler form as such. So the square root of 4 will give me the 2. And then the square root of 10, well, I can't simplify that any further. There's no other way to simplify it. That's as simple as it's going to get. So this is one of the main ones we're going to do. So what we're really doing is working backwards from the idea that the square root of a plus times the square root of b was equal to the square root of ab. So we're working backwards. We've broken 40 up into this form so we can get it down to a simpler form. But again, it's all about the perfect squares. If we can't get perfect squares, you can't simplify it. And that's okay if you can't simplify it. Not a problem. If I was given the square root of 15 there and trying to... I can't simplify that. There's no perfect squares that are factors of 15. So it can't be simplified. Square root of 72, however, can, because I can write that as the square root of 36, the square root of 2. So 36 is a perfect square, so square root of 36 gives me the 6. And then the 2. So we write it as 6 root 2. Again, we assume, like we do in algebra, that there's a multiplication sign there, but we don't write it as per our algebra. If we have a look at 6 times root 20. Again, we've already got 6 times the root 4 times the root 5, because we've broken 20 up, because we've got a perfect square of 4 that is a factor of 20. Again, if I don't have any perfect squares, can't do it, can't simplify it. So that gives us 2 times the root 5, 6 2s are 12. So 6 root 20 can be simplified to 12 root 5. And we've got 5 times root 3. Well, this is basically working the other way. If we get a question that says, well, write the whole thing as a surd, this is working backwards in the same idea, because 5 can be written as root 25 times the root 3, and 25 times 3 gives us the 75. So we can work it backwards sometimes. Sometimes it might be what the problem requires, or the problem asks us to do. So what do we got to think about? We're looking for we're looking for square roots every time. So if you simplify a surd, divide it into the 2 square roots, one of which is a perfect square. So we're looking for perfect square. Now remember your perfect squares here, they're the ones down there, and it's handy if you do recognise them. Just makes life a little bit easier if you can look at numbers and say, well, I know 4's a factor, or 9's a factor, 16, 25, 36, and so on. It starts to make life a little bit easier the more you can do that. And then also, you can use this rule, square root of AB is a square root of A times the square root of B. And remember, not all surds can be simplified. Like all algebraic expressions can't be simplified into one nice little term. Same idea, not all surds can be simplified. But we're going to use a lot of these, not only by themselves, but with a lot of problems we're going to face. And more notably, situations where we're going to add and subtract surds as well later on.